We're going to talk about 3.1 today. This is about limits, and it's a really important section, so there will be times that you probably will need to pause and maybe re-listen to what I say. Some of what we can do, we can actually look in our calculator at graphs to figure out limits. So that's what this first example is going to look at, is looking at a table. There are ways that we'll be able to do them algebraically, and so you're going to need to make sure you're comfortable with how to do the limits from all of the different approaches. So this first example, we have a parabola, and in our parabola we're wanting to see what happens as f of x, and so as my x value approaches 2, you can see here we have our two arrows, and we're saying what happens as we approach that value of x equals 2 to our y value. So you're going to be able to use in your calculator the trace mode, or you can also use the table mode that I showed you earlier. So we have two different notations, which you'll see below here, which talks about a limit as x approaches the a value from the left and as x approaches the a value from the right. Very important for you to make sure you have that notation down. So if I'm approaching 2 from the left, I put that minus sign beside the 2 of f of x, and that's what's represented over here in the pink. So this is as we go from the left. So as we go from the left, you should see that you're approaching the y value of 4. The limit as x approaches 2 from the right, which is the positive beside the 2, is the blue arrow, and as I approach the x value of 2, the y value is also approaching 4. We're going to learn if these two match, which means if I'm approaching the same value from the left and the right, then the limit as x approaches 2 exists. These two have to match for this to happen. So you have the definitions from the textbooks. Again, you can review this, you can pause and read over it, but the plus sign tells you you're coming from the right, and the negative sign here tells you you're going from the left. And we're talking about as we're approaching the x value, what is the y value doing? This is as I'm getting closer. This is not actually asking what's happening at that specific value, and that's something you have to break yourself of thinking. Sometimes it's going to match, but we're saying as we approach it, what do we approach? If they both match, then the limit exists. So that's down here in this box. So I'm just going to kind of summarize that down here. If the left limit matches the right limit, then the limit exists. They have to be the same. So let's look at example 2. So again, this is showing what you would see in your calculator. So I want to remind you something here. This is my function I'm looking at. This has a hole in the graph because I cannot have a denominator equal to 0. So I actually have a hole in the graph. And so if you actually blow this up, you'll see that there's actually a hole in the graph at x equals 2. It's harder to see when it's smaller. So remember, I don't care what's happening at that actual value. I am asking what happens as I get closer from the left and the right, and does it approach the same value? So looking at the chart and looking at the graph, we are approaching 4. Even though f of 2 is undefined, because there's a hole there. So I need you to associate. It doesn't matter what's happening at the actual value we're looking at. And I noticed here I just put f, and in the problem above it says g. Sorry about that. But we're saying, what does the y value approach as we get closer, not what it's actually doing at that specific value. So I'm trying to kind of show you right now some of those exceptions to the rules. So let's look at this next one, example 3. This one is actually what's called a piecewise function, which is going to be really important. You're going to have to graph a piecewise function on test 2. Okay? So piecewise function says we only have our function defined at different values for different pieces. So if we read this, we have a parabola everywhere except for x equals 2. If x equals 2, it tells you we have this value here. So notice there's a hole here, because that's the parabola for every other value, and here. So I actually have a hole. We do actually have a value that exists, but I don't care what that value is. Remember, the limit is what I'm doing as I approach it. So my limit as x approaches 2 of h of x is still equal to 4, because the pink and the blue arrow is still approaching that value. But h of 2 is 1. That doesn't matter. This limit is still what am I approaching from both sides. We're concerned as we get closer and closer to 2. So we're going to look at a rational function. So we know with a rational function from college algebra that we have asymptotes. We can never cross an asymptote that is a vertical asymptote. We can sometimes cross a horizontal, but we will always eventually approach it when we're getting to infinity or negative infinity. So in this case, when we look at this one, the limit as x approaches a negative 2 from the left, and the limit as x approaches 2 from the right. So approaching it from the left is what they have here on the pink arrow. So we're saying, okay, as we go closer and closer and closer, what is my y value doing? And my y value is going to infinity. Some textbooks would call this that it doesn't exist. I think it's better for us to label that the limit as x approaches a negative 2 from the left side, it's approaching a positive infinity, because this tells me it's going up. Looking at this from the positive side, the right side, we're going, following this here as we get closer and closer to negative 2 from the right side, we should see this is going to a negative infinity. Therefore, the limit as x approaches 2 of f of x does not exist. And the reason it doesn't exist is these two don't match. Limit is your behavior. To have it exist, they have to match from the left and the right. So look at example 5. This one is actually called a piece function. It's a where you're stepping stone for each piece. Okay. So in this case, this is hard to see because this is actually a graph from your calculator, and so this is just to clarify for you. If you look at this, x can't equal 0 because it's in the denominator. So there literally is an open circle at both of those spots. Okay. So f of 0 is undefined. The limit as x approaches 0 from the left, which is this piece here, is negative 1. The limit as x approaches 0 from the right is a positive 1, because remember it's the y value. These do not match, so the limit as x approaches 0 does not exist. Now on the test, it is not acceptable just to say it doesn't exist. If you're ever going to tell me a limit doesn't exist, you need to be able to explain to me why. And if I asked you to explain to me why, you would say the limit from the left is equal to negative 1, the limit from the right is equal to positive 1, and they do not match. So here's kind of a summary from the textbook about the existence of limits. So remember that I said some books write does not exist. We want to write infinities and negative infinities if they are both approaching that. So I want to clarify something here on the right hand side. I'm just going to draw this out for you. If I had something that looks like this, and I said what is the limit as x approaches 0, notice that both of these, as I approach x equals 0, both go to infinity. So this one would have a limit of a positive infinity. So this one would have one of infinity. if I had this graph and I said what happens as I approach 0, from the right it approaches a positive infinity, from the left it approaches a negative infinity, so this one does not exist. So this top one is equal to infinity because they both match, and if they both would have been going down, we would have had a negative infinity. Number 2 represents the case where they don't approach the same value, so there's no possible limit. And number 3 talks about the case where there's a jump in the graph. So at this specific value, on the bottom we're approaching a different value than we are on the right, so this would be a does not exist case. Please be careful. Just because there's a jump in the graph does not mean it doesn't exist. It depends on where you're looking at it. So we're going to end this little clip by looking at this example, which again comes from the textbook, and it just kind of highlights where some pieces don't exist and explains to you why. So here the limit doesn't exist because it's approaching different values at different spots, okay, from the left and the right. Over here, the limit doesn't exist because I'm approaching a positive infinity and I'm approaching a negative infinity. So this is a positive infinity, this is a negative infinity. They don't match. Over here, we would actually write down, for me, I would want you to write down the limit equals a negative infinity because these both do approach that. Some textbooks write that this doesn't exist, but we want to write the negative infinity portion of this. Looking at the other two that they've highlighted, this one works. Even though there's a hole, it's still approaching the same value from each side. Here, this limit as x approaches 4 still exists, even though it's not defined. Okay. So this is a great one to kind of just go back over, pause, and look at that.